Welcome to 1.6 inverse functions, and there's a video on the website, and if we were in class and we'd watch this video, it's maybe 15 minutes long or so, and it's a great Dr. Seuss video from a book called The Starbelly Sneetches, and it really illustrates inverse functions very, very well, and I'll be talking about that a little bit here, but if you know me, I like analogies for things. It helps kind of solidify in my mind what's going on, and so well worth your time to watch that. As you watch that video, you probably won't think that Dr. Seuss had inverse functions in mind as the theme of the show, but maybe just maybe he's got some mathematical background as well. So let f and g be two different functions such that f of g of x ends up equaling x. I need a picture. So we start with x, we send that through a factory named g, and once it comes out of that factory, we don't know what it is there. It doesn't tell us, but we do know that we're supposed to send that thing in turn into a factory called f, and what ends up happening is it comes back out x. Does that mean it must have stayed x here? No, this could have been gone from x, turned into a kangaroo, gone back into f, and come back out as an x. What we know is that f is undoing g. Whatever work g is doing, f is undoing. Or in this case, f takes x, changes it into something, but g just turns it right back in there. Much like if, let's say I've got 7x equals 14, we could divide both sides or multiply both sides by 1/7. Divide by 7 or multiply by 1/7, because 1/7 undoes the 7, and we get x equals 2. 1/7 and 7 are multiplicative inverses. X plus 3 equals 5. We subtract 3 because 3 and negative 3 are additive inverses. So that's what's happening with these. And we write that as like f negative 1 of x. We'd read this f inverse of x. Excuse me. So f of f inverse of x turns back into x. Or f inverse of f of x turns back into x. The key to really understanding, and this is going to seem so simple, but it gets overlooked a lot. If you ever have a question about inverse functions, basically this is the key. X's become y's, and y's become x's. If I have a function that turns 1's into 4's, and 3's into negative 2's, and 5's into 6's, let's say this is f right here, then f inverse would have to be a factory that turns 4's into 1's, negative 2's into 3's, and 6's into 5's. The domains become the ranges become the domains, because that's just x's becoming y's and y's becoming x's. Okay, now let's take a look at this. Let's say I had a factory where we're turning 1's into 3's, and we're turning 2's into 3's, and we're turning 4's into 5's. This, no doubt about it, is a function. I'll call it g. So then we'd say, well, what is g inverse? And we'd say, okay, I see. Well, in g inverse, we're telling the elf in charge of 3's to turn them into 1's. We're telling the elf in charge of 3's to turn them into 2's, and we're telling the elf in charge of 5's to turn those into 4's. Then we see this is not a function, because the elf in charge of 3's, there's elf confusion there. This could still be a relation. We have ordered pairs 3, 1, 3, 2, 5, 4, and what would that look like? We have 3, 1, 3, 2, and 5. Yep, 3, 1, 3, 2. So this is not a function because of this relation right here, vertical line test. So it's not a function. It's still a relation, but it's not a function. This is what my G inverse tried to look like. Whereas G back here look like this. 1s get turned into 3s, 2s get turned into 3s, 4s get turned into 5s right here. So this is a function, but it does not have an inverse function, because the inverse function, these 2 points right here, become an issue right there. Okay, that brings us to one-to-one functions. Now, I have to preface this, and don't want to upset anybody with with the analogy I'm about to use. I just think it's a good analogy, and we're right about at that time, this time of year, where either before this or shortly after this, we're approaching homecoming. We're starting to think about homecoming, and hopefully we're in school in 2020, and we're getting to think about this thing, and we're starting to think, well, maybe I should have a date to homecoming. And let's say, and here's my preface, I don't care who or what you go to homecoming as long as it's legal. But let's say for the purposes of this, that we're going to chart homecoming dates as a boy going with a girl. No offense intended. Does not matter to me one bit or the other, but the other way does not work for my analogy. So let's say boy 1 is going to homecoming with girl 2, and boy 2 is going with girl 1, and boy 3 is going with girl 1, 2, 3, 4, 5, 6. Boy 4 is going with girl 1, 2, 3, 4. Does that represent a function if there's only boys 1, 2, 3, and 4? Yep, every boy is assigned to a different girl, and no boys assigned to 2 girls. So that is a function. Now, if boy 5 is going with girl 1, is that a function? It is a function. Each boy, there's no elf confusion for boy 1, boy 2, boy 3, boy 4, boy 5. But it might be a little bit surprising to boy 5 and boy 2 that they're creating the same thing or going to homecoming with the same girl. So this is a function, but it is not one-to-one. Just like this was a function, but it's not one-to-one. And a function f is one-to-one when a and b in its domain f of a equals f of b implies a equals b. It just means it passes the horizontal line test. This one does not pass horizontal line test. Okay? And that has an issue for us when we're trying to find inverse functions. This is a function. This is a function, but it is not one-to-one. A function f has an inverse if and only if. That is a very strong tie. If and only if f is one-to-one. This is not one-to-one. It does not have an inverse function. It does not have an inverse function. It's not one-to-one. Okay, finding an inverse function, use the horizontal line test to decide whether it has a function or not. It has an inverse function. Does not have an inverse function. Is not even a function to begin with. Up until this one right here, past the horizontal line test, has an inverse function. But once I have that situation, no inverse function. And then after that, they're just talking about how we find inverse functions algebraically, and we are going to go ahead and just do that. So I think you'll see the explanation of that coming. Okay. Find the inverse function informally, which is a little bit strange to me. I'm going to go ahead and do this first one algebraically, and then you'll see why we could have done it informally. But that is definitely fraught with some dangers if you try to do that on more complicated expressions than this one. So don't forget, x's become y's, y's become x's in inverse functions. And f of x is a fancy name for y. So this is y. So y's become x's. X's become y's. Solve for y, and I get y equals multiply by 3, 3x. So I'm claiming f inverse of x equals 3x. All right. Now, it says show that f of f inverse equals x and f inverse of f equals x. Okay, let's find f of f inverse. F of f inverse is f of 3x, because 3x is f inverse, we're claiming. And f is a factory that takes things and multiplies them by 1/3. And we do get x. Now, one should understand this. F of g of x, the composition of functions, is not necessarily commutative. This is not true. However, for this case, if f of f inverse of x equals x, f inverse of f of x will also equal x. So you don't really need to do this both ways, and I'm fine with that. But as a general practice, the composition, it's like we know that a times b equals b times a. Those are equal. That's because it's commutative. But the composition of functions is not commutative. Okay. All right. So here's the dangerous one. So we say, well, okay, I get it. Then if all I got to do is undo that 1/3, multiply by 3, then I guess I just need to divide by 4 and add 1, or should I add 1 and then divide by 4? So there's two possible solutions to it. This is just my thought bubble. You don't need to write this down. I think I'm either going to be x plus 1 divided by 4, because I undo the 1, I undo the 4, but maybe it would be, I wonder if it's x, then divide 4, and then add 1. Just a little thought bubble here for this one. Well, let's see. Let's go through the process. X equals 4 times y minus 1. So y minus 1 equals, I'm going to divide away 4, x on 4. Oh, y equals x on 4 plus 1. F inverse of x equals x on 4 plus 1. So I think you can see the inherent danger in just going ahead in this whole informal process on this. Yes, this one is very safe. All we have to do is rescue times 1/3. So we're going to divide by 1/3 or multiply by 3. In this one, no problem. F inverse of x equals, there's only one step. I need to get rid of the 7th power, so that's the 7th root. But in this one, a little bit dangerous. Imagine if there were 3 or 4 steps. We have to get all of those orders correct. So that's where we would change x's into y's, solve for y. Okay, so I need to show that f of x on 4 plus 1, f of f inverse, let's see where that gets us. F is a factory that takes things, in this case, x on 4 plus 1, subtracts 1, and then multiplies the result by 4. So we get 4 times the plus 1 minus 1 cancel, and we get x, and we got it. And here I have to show that f of 7th root of x, f of f inverse, this is f inverse, well, f is a factory that takes the thing, 7th root of x, takes it to the 7th power. Oh, of course, that's x. We've got it. Only have to do it one way. Now, 15 through 18, we got matching problems here, and we could seriously do this just in a large part just by, well, it sort of looks like kind of thing. Like 17 sort of looks like A, and 18 sort of looks like D. Now we have a line and a line. There may be some thought going in there, but let's take a look at it this way. In 15 appears like it turns zeros into negative 1s. So I'm looking for a graph that turns negative 1s into zeros. Negative 1's not 0 here. Negative 1's not 0 here. Negative 1 is 0 here, it looks like, and negative 1's not 0 there. And maybe just for reference, it appears like if 2, 3's not on there, it's pretty darn close. How about 3, 2? 3, 2. Well, 3, 2 is close here. 3, 2 is not close here. 3, 2 looks like it's right on the money here. So I believe this one's C. 17 turns zeros into ones most definitely. So I'm looking to turn ones into zeros. 1, 0. Yes. 1, 0, no. 1, 0, no. 1, 0, no. That's the only one it could be. Now, just for the sake of it, it looks like this one might turn 2s into about 4s. Oh, that was this one up here, 2s into 4s. So if this one turns 2s into 4s, I'm wondering, are 4s getting turned into 2s down here? 1, 2, 3, 4. Well, it's certainly, is that right? 1, 2, oh, that was a 3 into a 4. Sorry, I went 2 from here. I went up to here. 3 gets turned into 4. So does this turn 1, 2, 3, 4 into about 3? Yeah, that seems pretty reasonable. 17 is A. Okay, a lot of explanation on the first page. The front page, the new rules. I suspect this page for you to get the homework done is only going to take a few moments. So stay tuned. Ask whatever questions you can.